The views expressed here do not reflect the views of our respective employers. Hello and welcome to SPEXcast, a podcast about the science and technology of space exploration. My name is Phil, and I'll be your host today alongside TJ.
Hello.
SPEXcast is made for space fans like you. Check out space news and mission deep dives on our website, blog.spexcast.com, and join the space discussion on forum.spexcast.com. You can also send us a tweet at SPEXcast or send an email to spexcast@gmail.com. The Spectro-Photometer for the History of the Universe, Epoch of Reionization, and Isis Explorer, or SPHEREx, is a 2-year science mission designed to survey the cosmos in 96 color bands, mapping the whole sky once every 6 months, and all of this data will be publicly available. The mission was recently selected by NASA's Explorer program and is targeting a 2023 launch. Today on the show, we're speaking with Dr. Michael Zemcov of the Rochester Institute of Technology. Dr. Zemcov is an assistant professor at the RIT Center for Detectors and one of 19 co-investigators for the SPHEREx mission. Dr. Zemcov, it's great to have you on the show.
Hi, thanks. Thanks for having me.
So to get started, can you describe the mission architecture of SPHEREx?
So the mid-X class missions are sort of in the middle of the road in terms of, orbital size missions that NASA does. It's the largest principal investigator-driven mission that NASA will do, at least in astrophysics, meaning that it many of the bigger missions, for example, JWST that you hear of, those are sort of more run by committee, and they don't really have principal investigators per se. They kind of have steering committees and so on and so forth. So Jamie Bach is the PI of SPHEREx, and he's basically ultimately responsible for the whole thing. So it's like having a general in charge instead of, a committee. In terms of, size, weight, that sort of thing, it's a few hundred kilograms, including the spacecraft bus, and about the size of a desk, I would say, is the closest thing I can think of. The telescope itself is tiny. The primary aperture is about 20 centimeters, and it has 3 mirrors and then some beam splitters and then some filters. So when I think about the actual telescope, I think of something about the size of a suitcase. And then when you actually look at a picture of the thing, it looks like it's surrounded by an umbrella. What that is heat shields that are letting the telescope passively cool down to about 45 Kelvin, which we need for our detectors to work. And in fact, the mid-X design is designed to fit into a fairing for a Pegasus XL, though we may go on a Falcon 9. We don't know yet.
Very cool. Can you describe what kind of orbit that SPHEREx will be in?
So SPHEREx is going to be in a Earth terminator orbit, which is basically the sunrise line, and it kind of follows that around and around and around over time. The reason for that is basically we never want the sun to be able to view the telescope directly, because of course then it heats it up, right? You get the full sun loading, you'll suddenly get the telescope up to 300 Kelvin. So the idea is that if you go on the sunrise line, you can basically tilt everything so that the sun never sees into the heat shields, and we can radiatively, cool the internal stuff to space.
What are the science objectives of the mission?
The problem with SPHEREx, or the nice thing about SPHEREx, I guess it's not really a problem, it's a feature, is that it will do a whole lot of things. So the concept here is to map the entire sky between 0.75 and 5 microns in resolution of like 50 up to 150 spectral elements over that whole wavelength range over the whole sky. And the things you can do with that kind of data set are truly phenomenal. We can talk about that later, I'm sure we will. But the things that our team decided we were most interested in are 3 things. We want to do inflation, which is the earliest moments of the universe after the Big Bang. Cosmologists like myself think that the universe underwent a very rapid kind of explosive expansion, and then for whatever reason decided to stop. And what that did was it made quantum mechanical scales blow up to cosmic scales, and that explains a variety of things we see about the universe. And one of the problems with inflation is there's not a lot of ways to get at it. So SPHEREx is one of the few kind of promising leads we have where we might be able to sort of understand these early moments. Another of the science cases is to understand the evolution of galaxies over cosmic history. And we do that basically by the fact that it's a spectral instrument, so we can really kind of map out what the energy output of galaxies is. And if we have some idea of where we are, which we will because we will be able to determine distance very well, we can kind of map that statistically out. And then the final thing is we're looking for water ice. So and that's going to be in the Milky Way, around young stars and stars that are currently forming. So that's really the three prongs of SPHEREx that the science team is pursuing.
All three of these science objectives will be using the same set of data?
Yeah, so it's designed to be a surveyor. So really, as it's going around the Earth in this Terminator orbit, it's picking up sort of like 6 fields as it goes around and observing deeply, and then switching to another field, observing deeply, and switching to another field and observing deeply. And the idea is that if you pick which fields you're looking at over time, you can build up a map of the whole sky. So that's really the sort of concept here, is to make a data set that is this kind of catalog or complete set that is a little bit different than what Hubble or JWST is capable of doing.
Right, like a comprehensive map of the night sky in these bands.
It's an all-sky map, and we've done lots of all-sky maps before. NASA has, for example, Planck and WMAP, and then going way, further into the past. But I think this is the first sort of comprehensive all-sky map with this resolution at these wavelengths.
Great. And that's brings up a great question. So we know about WFIRST and James Webb, which are both going to be space telescopes looking in the infrared. But how does SPHEREx and SPHEREx's goals fit into the broader astronomy ecosystem alongside these other existing and proposed missions?
So the interesting thing is that SPHEREx has a lot of synergy, and I think part of the reason that it was selected is that it has a lot of sort of complementarity with these other things. So, for example, JWST is really, really awesome at drilling very deep and having really high angular resolution on a really small patch of sky. But the problem is that it has a finite lifetime, and it is really not going to be able to map anything like the whole sky. You're going to have to point at things you're particularly interested in. So, certainly astronomers have some idea of what they're already interested in, but if you have a data set like SPHEREx, it really opens a lot of doors in terms of finding interesting objects that are sort of outside the norm. We haven't really had a data set like the one SPHEREx is going to produce where we can go out and sort of say, oh, wow, that's a really weird galaxy, or that's a really weird protostar, or whatever. And I think that matches with what JWST is really strong at in a nice way.
So the spacecraft will be collecting a lot of data. What data is kind of going above and beyond these three objectives, which you might consider be bonus data that other researchers who, once they get access to this data set, could make different observations and different inferences with? Oh
gosh, well, so these kind of missions don't sort of spring from the ground at the time that they get selected. And in fact, I've been working on SPHEREx since, about 2013. That was sort of the inception of the idea. And in the time between then and now, so I guess it's been 6 years, we've had a couple workshops, community workshops, where we invited astrophysicists from all different branches of astrophysics to come and say what they're interested in. And I couldn't give a complete set, but just to give you some idea, we have people on the team who are very excited about looking for asteroids and for Kuiper belt objects and other sort of solar system objects. We're going to do a really good job measuring the zodiacal light, which is the diffuse dust that lives in the plane of the ecliptic around the sun. And so there have been a variety of missions that have mapped that out over the years, but SPHEREx will get really, really nice signal-to-noise on very fine spatial scales and be able to ask questions that we haven't been able to ask so far. Going further out, SPHEREx is going to be a very effective brown dwarf finding machine. So brown dwarf stars are stars that aren't massive enough to really support fusion on their own. And so think of something, bigger than Jupiter, but much smaller than the sun. They still sort of have heat, and they still might generate a little bit of heat internally. One really good question is, what's the population of these things? How many do you get, in the galaxy? And the WISE mission has given us, a good answer, or at least the start of an answer to that. SPHEREx is going to be really, really good at finding these things. So, mapping out what are the very massive planets or slightly sub-star objects that exist in the galaxy is a really good question. Further out, it's going to be good for sort of comparative time domain astronomy. So we'll be able to go back every 6 months and sort of compare, has this field changed, and we'll have a pretty good signal to noise ratio on whether a given star or AGN or whatever it happens to be has changed at all in that time. And I think that the questions about things like galaxy clusters and galaxy evolution, these are really going to be open. There's just a whole bunch of topics that will just be available from this data set. So
yeah, that's a lot of exciting things. For our listeners at home, AGN is a active galactic nuclei.
These are supermassive black holes that live at the center of galaxies and are actively in the process of accreting matter, and as a result of that, they spew out these big jets that have these very, very high velocity particles in them. They're kind of like nature's particle accelerators, and they have really, really high energies. So they're interesting for a variety of reasons, having to do with how supermassive black holes operate and how galaxies are coupled to how supermassive black holes, or at least the supermassive black holes in their center.
Mm-hmm. Is there anything else unique to SPHEREx as a spacecraft and also as a science mission?
Well, I think one thing that's really cool is that this is a very compact instrument. We have 6 detectors on there, and these fancy what are called linear variable filters, which are filters that change their transmission characteristic across the face of the filter. So what you can do is you can put that in front of a detector array right up close. And what it means is a pixel on one side of the detector array is going to read blue, and a pixel on the other side of the detector array is going to read red. And what that lets us do is it kind of lets us build up over many exposures the complete spectral information. It's a very clever solution because it doesn't really require any moving parts or any fancy optics. So it's really low risk, which is kind of a cool thing.
Yeah. And what that means is that instead of taking a fixed snapshot of all the data, the satellite's actually taking composites that are slightly offset, and once the full frame has moved left to right, you have all of the spectral information in that picture.
Yeah, you got it exactly. Yep. Another unique thing, or somewhat unique, is the entirely passive thermal design. So a lot of spacecraft use heat shields, but not so many have been entirely passive, where they sort of the only way they cool themselves is by not pointing at the sun. The most recent probably that people might be familiar with is the Spitzer warm mission. So Spitzer was an infrared great observatory that NASA flew about the turn of the century, and it had a very excellent career as a cryogenic mission, but then they ran out of cryogens. It ends up that some of the instruments were capable of working at temperatures that this telescope sort of floated to just by sitting in ambient space. And they were able to use that effect to keep the mission going for quite a while. And in fact, it's still going. It's going to finish probably this year. SPHEREx is not the first mission to have used this concept, but it is the first mission I'm aware of that is entirely dependent on it and is designed around it.
So kind of doing a deep dive into the weeds of the science mission, why is SPHEREx observing these bands in particular, and how do they actually allow astronomers to interpret things like the history of galaxy formation and planetary formation, which exist on completely different scales?
So it's a fact of how the universe works, or how physics works, that when you make a star, the typical temperature of a star is in the many thousands of Kelvin. And as a result, stars look more or less like black bodies. They have some features on top of that, but the broad, like thinking about how it, how a star looks over wavelengths, it looks more or less like a black body with some characteristic temperature. And it ends up that those temperatures have the black body curve peak in the near infrared and optical wavelengths, depending on the temperature. It's a black body is a curve that if you have a black thing at a certain temperature, it will emit photons at a characteristic energy, density, basically, or spectrum that tells you exactly what the temperature was of the source you're looking at. So the point is that stars emit most of their light in the near infrared. That's just a fact of how stars work. So if you're interested in mapping out the structure of the universe as traced by stars, you would just pick these wavelengths, because stars are not bright at other wavelengths. So it has to be something in sort of like the near infrared optical. Now, thinking about the inflationary science case, which I'm particularly excited about, how's that going to work? Well, the concept is that inflation sort of set the initial conditions for the large-scale structure of the universe. So a certain kind of inflation makes a universe that looks a certain way, and a different kind of inflation makes a universe that looks a different way, and that's how you could kind of tell the difference between them. We think we understand the equations that govern how large-scale structure sort of forms and evolves over cosmic history really, really well. If we have a reliably good map of where the stuff is in the universe, basically run the equations backwards and back out what were the initial conditions. What did inflation impose on the universe? So if you want to map out galaxies, there's a few sort of wavelengths where that would be sort of obvious, but one obvious place to look is where the stars are, right? Because that's what a galaxy is. So if you think that the sort of large-scale structure of the universe is traced by where galaxies are, we might as well look for the stars, and that's kind of the concept of SPHEREx. So what we're going to do is basically look at the position of all the galaxies in both, X and Y on the sky, but also distance, and then basically use that information to constrain what were these initial conditions. We get the distance by basically saying, okay, well, we know what the energy distribution or energy output of galaxies looks like. Now, they can look a bunch of different ways, but the point is, those are kind of understood, they're templates. So what we can do is we can take sort of a library of what galaxies look like and then fit against that and say, aha, well, this spectrum looks like this galaxy really well. And we know that we had to shift it by a certain distance. And because of cosmic expansion, which basically imposes a shift in spectra of sources if they're very distant, we can say, well, we know how distant it is. And it ends up we're going to know that distance to about 1%. So that's sufficient accuracy if you have enough information that you can back out this inflationary science. It's a similar argument for the history of galaxies, because galaxies, one way of thinking about what a galaxy is that it's just a bunch of stars. And if you kind of have that model in your head, well, you can say, well, so I know how stars emit, and I know what the sort of features from the various elements in their spectra, impose on the spectrum of the galaxy as a whole. And you can go out and search for that. So you can basically constrain things like how quickly is this galaxy forming stars, how big is the galaxy, how distant is the galaxy, all that kind of stuff. And, by combining all that information, you can get a pretty accurate history of like what was the, characteristic emission of the average galaxy or even all galaxies over cosmic history.
And what about ICEs? I understand that stars can behave like black bodies, and if you know what stars look like, you could look in the infrared. But what about looking at ICEs?
So that's a good question. So the ICE targets we're looking at are a little bit different. They're not actually necessarily even stars yet. And if they are stars, many of them are going to be really obscured by dust and they're not going to look like a star. So the concept there is that we don't care so much about what the spectrum of the star is. As long as we know that there's something there, we can say, okay, well, there's something there that's interesting potentially. And then what ice is it's a spectral feature. So specifically water ice, we're going to look for other kinds of ice too, but water ice is possibly the most interesting. What we're going to do is say, okay, well, we have some smooth curve that's the intrinsic spectrum of the source, and then we have these dips at these known wavelengths. And of course, stars in the galaxy don't really redshift very much because their velocity compared to us is relatively small. So those features, those ice features in the spectrum are going to show up, very well-defined places. And the real question is, how wide are those features? What's the shape of those features? And that can tell us about the state of the ice and what its temperature is and interesting things like that.
So you've spoken to astronomers about how they might use SPHEREx data, but what aspects have stirred up the most excitement in terms of the scientific community from the people you've talked to? Like, what are the astronomers most excited to see?
SPHEREx is one of those really cross-boundary things. I'm not sure I've ever worked on something like this before, where every single astronomer I talk to, once they sort of understand what the data set's going to look like, goes, holy smokes, I could do so much with that. In whatever their little, field of expertise is. And I think that's really the power of the data set, is that it's got this huge legacy value, that it's so complete and ideally, so constructed in a way where it's all kind of similar, that it's going to have a lot of value because people will hopefully trust it and be able to use it for whatever the heck they decide they want to use it for. And I don't think there's one thing that stands out to me because, again, it really depends on what that person is interested in. But I'm not sure I've met an astronomer who kind of yawns and says, yeah, okay, not very interesting. I don't think I'm going to use that. So I really do think it's sort of cross boundaries in an interesting way.
So next I'd like to go into the weeds in terms of the spacecraft itself. So you mentioned SPHEREx, the instrument, will image the sky in a bunch of these different wavelengths using a linear variable filter. Can you explain how this is different from other ways of getting the spectral information? Like, you're not using complex mirrors, you're not using a diffraction grating. So what are the trade-offs here, besides linear variable filters not having moving parts and some of the other things you mentioned? Are there other disadvantages to LVFs?
The issue here is, how do you disperse light? And the ways that we sort of typically disperse light are with prisms or with gratings. And the drawback of both of those things is that you can't get spectral information and spatial information simultaneously, or at least it's really hard. And the reason for that is, if I have a source sitting next to another source and I disperse the light with one of those sort of traditional dispersion mechanisms, what I'm doing is I'm scrambling up the light, right? Because the light gets dispersed spatially. It goes from red to blue across the image at the focal plane. It's not just a single dot anymore. You're taking that light and you're spreading it out. So if I have two things next to each other along the line where that dispersion happens, their spectra gets all scrambled. And so what you typically have to do is put a kind of mask of some sort in the optical system so you can really restrict down to just the sources you're interested in. And that's okay if you know where the sources you're interested in are, but if you're trying to do something like measure the spectrum of every point on the sky, it gets a little complicated because you're always going to have, stars and galaxies, whatever, that are dispersing their light into neighboring black areas, and you just really have no idea how to unscramble it. It's a really complicated problem. So the nice thing about an LVF is, although it comes at the cost of having to sort of march it around and take different pointings to fill in the data cube, you really get the opportunity to be entirely unique about which source is which photon coming from in your image. So if you had a way to do that with the sort of more traditional gratings and prisms, they would be equally fast, but the problem is that they kind of don't work that way. So that was the sort of step when it came to SPHEREx is, gosh, if we just use this, relatively simple technique, we can be really effective at mapping. And that's really a synergy between the way that the LVF works and the way that these near-infrared detectors work, where a near-infrared detector is a kind of photo detector where you have to point it at a spot on the sky and wait while it sort of integrates up photons. It builds up photons. So it's not really the kind of detector where you can kind of scan it around the sky actively and just build up integration over time that way. You have to kind of be a little bit more, pointed about it. So that was kind of the realization that it's the combination of the detector with the LVF that makes it really efficient to use in this mode.
Okay, so we talked about the LVF and you mentioned the detectors. SPHEREx is going to use two sets of Hawaii 2RG detectors, which are CTDs that have a fair bit of history with spaceborne imagers. Each H2RG is a 2048 by 2048 pixel array. So that's, 16 million pixels for every collect. And then you rinse and repeat for the untold number of captures that are going to be required over the entire mission life of the spacecraft. What does the pipeline look like to handle all of this data?
Well, that's a good question. So one thing is that the 4 focal planes is the older SPEX design. The MIDEX design that we're baselining now is going to have 6. So all those numbers just got 50% worse. I guess the sort of good news as far as the pipeline goes is that it's really like an assembly line. It's not the kind of thing where you can afford to worry about each and every pixel independently because you would never be able to shovel the data. So a lot of the pipeline work that we've been doing has been focused around figuring out what are the sort of measurements and techniques that we have to apply so that we can kind of pipeline this data faster than we take it. So we take an integration every roughly 100 seconds. And what that means is if you can't process integration faster than 100 seconds when it gets to the ground, then you're kind of in trouble because you're going to be analyzing data slower than you're taking it. So the pipeline, fortunately, is pretty well understood. There's a bunch of steps in it. It's not trivial, but it is all sort of addition, multiplication, subtraction, that sort of basic operation. So in general, it's fast. And really the hard part is just the data volume, is all the reading and writing to disk. So, one thing is we have to kind of minimize all that and try and keep as much in RAM when we've actually read in a file and kind of process it all the way through. I guess the other feature is that we're going to have to spend a lot of time before the mission figuring out how we're going to understand the data, because once the mission is launched and goes through its month-long commissioning phase, that's it. You better have everything in place because you have no more time to develop by the time it's actually making data. You're going to spend all your time trying to understand all the quirks in the data and then fixing it and trying to iterate. So it's fortunate for us that we're not having to do anything that's computationally too intense, at least at the sort of low level of making images.
So how are you going to convert a bunch of single images with many bands into one multispectral composite image of the sky?
I'm not sure we'll ever make one big image of the sky. At least we haven't proposed to. Not that we couldn't if we wanted to, but we're thinking more along the lines of catalogs. What we really want to deliver to people is there's a source here, it has a certain signal-to-noise ratio, and here's its spectrum. That's a little bit more handleable just because there's plenty of patches of sky that are black and, not terribly interesting for most people, at least. The actual sort of process is relatively easy, right? You just have a lookup table that says this pixel is looking at this color, and then you just go each time each position that was mapped to some particular source on the sky, you go pull all the images that position fell on the array, and then you know what wavelength each of those times was, and then you can just build up a spectrum that way. It's a large databasing problem, but it's not terribly difficult sort of intellectually, I think.
So you mentioned before that this satellite's going to be in a Earth terminated orbit, always in sunrise or sunset, but the mission length is about 2 years. You plan to measure the entire sky each in 6 months. So how do you go about doing that while still avoiding the sun?
So if you think about in 6 months, the Earth has moved halfway around the sun, which means that if you're restricting to positions on the sky that are at 90 degrees to the sun, that you can basically map out 360 degrees, because on one side of the Earth, you're seeing, one part of the 90 or one part of the 180, and the other side you're seeing the other part of the 180. And then as you move the Earth through 180, you're filling in that 360. So we should be able to map the sky once every 6 months that way. The reason for 2 years instead of 6 months is we want to do some data redundancy checks. It's very important in this kind of thing to make sure that when you go back to a source, you get the same answer every time. And our strategy is to sort of mitigate systematic errors as much as we can in design, but there's always systematic errors. So 2 surveys is a lot of it to basically, 4 surveys, I should say. A lot of it is to build up a understanding of the sky that's redundant in a way where we can make sure that we believe the answer. There is a certain advantage also to the signal-to-noise ratio, but of course, 4 visits, you're only getting error bars that are smaller by a factor of 2.
Are you including all 4 complete surveys as part of the data products that scientists can use? Will they be able to use this temporal aspect of it, or are you only using it for calibration and reducing your errors?
No, I think the plan is to release, each survey as it comes out. So the people will certainly have access to this temporal aspect. And, one interesting sort of thought experiment is, what if you're interested in asteroids, right? Those are going to be moving across the sky, relatively quickly. And you're not going to see it 6 months later in the same spot. So, and in fact, you're going to see it kind of moving in a way where finding it is going to be a little tricky because it's going to be at a different wavelength each time. It's not going to map in any sort of smooth way compared to the cadence of observation. So, I think that's like an interesting problem for the student, really, which is, if you're interested in that kind of thing, go and find it and figure out how to make it work. It sounds like a fun problem to me.
So one of the main advantages to SPHEREx's spacecraft design in the proposal is most, if not all, of the components have already been flown before or are flight ready. So obviously this buys down risk, but does it also limit the potential performance of the instrument by not using the newest, latest, and greatest technology?
So that's a great question. So what's the latest and greatest technology here? Well, passive cooling is passive cooling. So if you can hit your target temperature, you're done. Going colder doesn't really buy you much. So there's no advantage there. As you know, Phil, telescopes basically scale with the cost of the mission. So if you want a bigger primary aperture, you have to pay for that. And it's not a slow scaling. It's like a power law. So there's not a lot of wiggle room in terms of how big do you make the optics. you could imagine fiddling with the wavelength range. So we're going out to 5 microns. Newer detectors that are being worked on at the University of Rochester, for example, are able to go out to 10 and possibly even longer wavelengths. But they're very low TRL, so, we would take some risk there. And really, that's it. The spacecraft bus is, made by Ball, and it's kind of off the shelf. There are no moving parts. The star tracking cameras are off the shelf stuff. So it's not clear where you would want to, improve the technology. Perhaps in the detectors, the newer detectors are actually 4K by 4K, for example, but their pixel sizes are about 10 microns instead of 18. So basically, you're getting a smaller pixel size. So, if you think about, are you gaining much in terms of area or whatever? Not really. The spectral resolution of the telescope is limited actually by the telescope a little bit more than by the pixel, or at least they're sort of compatible or comparable. So would smaller pixels buy you more? Yeah, probably not. They might actually make the noise worse. So, this is really an issue of like the right thing at the right time, I think.
So on the other hand, you mentioned that there's no moving parts. All these things the problems with them are well known because they've been around for a while, for example. It seems pretty robust. Does that mean that this spacecraft could potentially have extended missions beyond its initial 2-year lifetime? Is that something you're looking forward to or expect?
Yeah, so one nice thing about SPHEREx is that it's not really limited by any moving parts. And in fact, the expendables, I forget the budget, but the propellant required to keep it in orbit will last, tens of decades, I think. So a good comparison here is WMAP. I don't know how much you guys know or remember about WMAP, but WMAP started out with a 2-year mission at L2, and they had a similar thing. They had no moving parts, and they were basically limited by the propellant that would keep them at L2. And that was another case where they had like tens of decades of propellant to keep them in their orbit. So they could just keep going. And in fact, they went on going for 8 years. And basically what ended up stopping the mission was that the scientific return, the reduction in error bars they were seeing was kind of diminishing returns because it goes as the square root of the time. So, once you get to 8 years, to get another factor of 2, you have to go 16 years. And then, it's a question of like, is it worth the cost of operations? Because these things aren't that cheap, especially, there'll be newer missions coming down the pipeline at that point. And, so that's definitely something that's been on our mind, that we would consider an extended mission if it was justified. But I think, this is one of those things where you have to see how you do and then deal with it when you get there.
Kind of switching to your personal connection with the mission, what is your role or area expertise on the SPHEREx project?
Right. So I did my postdoc in the cyber missions, which were sounding rocket. It was Cyber 1 was a sounding rocket that was working at these wavelengths, and it was looking at the fluctuations in near infrared background light. In a lot of ways, it was the genesis for SPHEREx. So, in fact, in the early days, when I was still a postdoc at Caltech, I was tapped to be the instrument scientist for SPHEREx and continued in that role for a while. The sort of, ups and downs of SPHEREx over the years are kind of boring, but the point is, at some point, I had to put that down and come to RIT and pick up my work there. And as a result, it's going to be pretty difficult for me to do much in terms of hardware, just because a lot of the hardware is going to be done at JPL, and, for obvious reasons, they like to keep that in-house. So a lot of my role is going to be in the data analysis, because I have a lot of experience analyzing data from detectors like this, for science like this, and I think I have a pretty good grasp of what the pipeline is and needs to do. So there's a small team of us on the mission, Brendan Krill, myself, Matt Ashby, others, that are really focused in on starting the data analysis. And we want to start that, as soon as possible. In fact, we've already started, because again, once it launches, that's a fire hose. I've been on orbital missions before, and you just don't have time to adapt or change anything at that point. You're really just in reaction mode. So a lot of what I'm thinking about is how do we deal with the fact that photons come in the telescope and then a bunch of stuff happens to them and then numbers get reported to us. And how do you undo all that properly so that you can make a good image and then subsequently a catalog of sources on the sky that you can hand to people and they can believe and do science with? So that's my main role at the moment.
Can you tell us a story about how you first heard about the mission and when you first got involved?
Oh, gosh. So the thing about this is I feel like I've been pretty involved from a pretty early stage. The genesis of SPHEREx goes all the way back almost 10 years to a little mission we proposed called Zebra. And the idea for Zebra was to piggyback a little telescope, teeny tiny telescope, out to Saturn. And what we would try to do is understand zodiacal light and the extragalactic background, things like that. And that instrument got rated very highly by the reviewers, but unfortunately its ride out to Saturn, which was a planetary mission to go look at Enceladus, was not selected. So, game over, right? But I think, thanks to Jamie Bach and Olivier Doré, the project scientist, and a few other of us, we kind of kept thinking like, what can we do with a really small telescope? Can we do, these kind of science cases? And the initial thought was to do the galaxy evolution stuff, because that's a little bit more what Cyber does. Until Olivier Doré and Chris Harada and Phil Mouskoff and other people pointed out, oh, hey, if you build an instrument that looks like this, it's going to be really good at figuring out where galaxies are. And with that, you turn that around. What can you do with knowing where galaxies are? This inflation. And as soon as that penny dropped, this got a lot more interesting because, as I mentioned, inflation is, one of the holy grails of cosmology right now. We really don't know very much, or if anything, really about it. We think it happened, but we don't have any sort of quantitative data to support that, other than sort of coincidences we see about how the universe works that we can't explain easily other ways. So once it was kind of a little bit clearer that, like, oh, yeah, we can really understand what's the three-dimensional structure of galaxies, it was kind of like boom, 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 boom. And, Jamie did a lot of work up at JPL kind of doing preliminary designs about how this telescope might look, how big it is, how would you do the spectral dispersion, and sort of connecting the dots that this LVF thing could kind of, be complementary to the detector in a way to really enable it. I think that was kind of the history of the thing. So, when I think about, like, when did SPHEREx kind of start, in quotation marks, I think, we had a science meeting in, 2013, something like that, where I don't know how much you guys know about how these things get made, but it was basically like a brainstorming session. So, Jamie got, as many smart people as he could in one room, and I happened to be able to be allowed in the room, and kind of said, okay, guys, like, what if we made a mission like this? What could we do with it? And that was kind of cool. And so that's where things kind of started. And since then, it's been kind of a question of refining the concept more than anything.
So kind of along those lines, once that mission kind of came together, 6 years ago, has there been any significant changes along the way to go to what got accepted by NASA and what's going to get built?
Okay, so you're going to get the whole history now. So let's see. In the beginning, I can't even remember. The beginning was a bunch of weird optical designs, and eventually we settled on LVFs as being something workable. There's really only one game in town in terms of the detectors that people use at these wavelengths, so we were kind of going to use those. There's different flavors, but it was pretty obvious, the basic architecture. And then, once you know what detectors you're working, what temperature you need to work at, And then it's a question of, do we build cryogenic stuff or do we not? And we eventually figured out that we didn't want to use cryogenic stuff because it's a pain in the butt and it limits your mission lifetime. So if you can get away without it, you're better, and we did. And so what ended up happening over the next sort of 2 years after that first meeting is we kept sort of refining the idea and kind of, trimming off fat and making it simpler and making it more robust. That's kind of how these things go. Until we were left with SPHEREx, which is the one that Phil was talking about, which had 4 bands and otherwise looked very similar to what we're going to build. So that got submitted as a small explorer, which is a slightly lower budget mission in the same explorer class in about 2016, if I recall. And it was down selected for a phase A study, which is where NASA throws $1 million at you and you get to refine the concept some more, and then you write it all up and you send it back to NASA, and they do that for 2 or 3 missions, and then select one based on that concept study report. And at that time, we heard that we were declined, which was a bummer. But just before we heard the results from the concept study report, we went back and submitted basically the same mission as the MIDEX, which is the slightly larger cost cap. And so we were declined. They picked an X-ray polarimeter for the SPECs. But again, we were chosen for phase A for the MIDEX class mission. And so we did another year and another big study, returned the materials back to NASA, and we felt a lot better because SPHEREx, even though it was basically the same sort of thing, SPHEREx as a SPECs didn't really fit that well. It was a bit of a squeeze to get all the science budget in. As a MIDEX, though, the cost cap's a lot higher, and it fit a lot better. It made a lot more sense. So we felt kind of good about that.
What are some of the trade-offs that you had to make in order to go from a smaller to a bigger craft?
There's not a lot of change to the actual hardware, to be honest with you. We figured we could fit 6 focal planes instead of the 4 focal planes, for example. That was a kind of late change. But in terms of like the bus and how big it is and how massive it is and all that, there really weren't that many changes. It didn't really incur much difference in terms of like the fundamental specs. So that's just a example of where more money will buy you better stuff, but you can fit it into the same package.
So along the way, what was the most challenging aspect of the mission to design, and why?
Challenging to design and why?
You can speak about for you personally, or which design aspect did you iterate on the most until you finally got it right?
Well, I think the thing that we got a lot of flack for was the passive cooling. So the passive cooling is these like umbrella things that are basically sunshades, and there's several of them because you can kind of get to progressively colder temperatures that way.
James Webb is also using this type of umbrella type cooler, right?
Exactly. Yes, James Webb is exactly using this type of cooler. And earlier on in the mission, we were going through reviews where they're saying, I don't know, that deployable looks a lot like Cassini's high-gain antenna, and Cassini's high-gain antenna didn't deploy, so are you sure it's going to deploy? And, we've never built a fully passive system before. Are you sure that it's going to actually reach its base temperature? And stuff that it's like, it's hard to argue because it's like, well, look, it's fundamental physics and we think we know how to do physics, so we can do calculations and like show you the results and we think we're going to hit that. So yeah, I mean, if it doesn't deploy, I don't know what to tell you, right? So I feel like we took a lot of flack for this sort of umbrella passive cooling thing that was probably undeserved, but NASA's pretty conservative, or at least the people who have to make decisions.
So personally for you, what aspect of the SPHEREx mission or spacecraft excites you the most?
What excites me the most is probably the inflationary science. Like I said, I'm a cosmologist, so my primary science area as a scientist is understanding the large-scale structure of the universe and the history and how did it get to be the way it is and all this kind of stuff. And I think it's been pretty clear to us for a long time that inflation is really hard to get your hands on. It's leaves fairly subtle imprints that are sort of, how to say, smoking guns that are like, oh, you could not have got that any other way. So being able to, constrain inflation, and maybe more interestingly, be like really, really good at constraining inflation, better than other things we're thinking of building, that's very exciting. I think that's, depending on what we see in, politics and yada, yada, that's kind of Nobel Prize worthy level science. And not that I'm saying we're going to win one, but I think that in terms of like excitement, that's really cool. That's something quite unique.
So what's next for the team from a preparedness standpoint, and then what's next the step for development of the spacecraft?
Launch is supposed to be in late 2023. The thing about explorers is that they're pretty tight on money, and so you can't delay that or NASA will cancel you. So it's going to be pretty much late 2023. A lot of the designs have been made, and now it's really a question of like really refining it and dotting the I's and crossing the T's more than anything. The next step is basically to start the detailed design, and then the fabrication, and then calibration, and then flight, and all that has to fit into 3-4 years of time. So it's a bit compressed. And then, while that's all going on, for me personally, I'm going to be spending a lot of time, with my research group at RIT, thinking about, okay, how are we going to analyze these data? What's that going to look like? Building routines, doing simulations, and making sure we can do it. And making sure that we can sort of deliver products that are the quality that we told NASA we would deliver. So those are kind of the next steps.
So for people who are interested in stellar and galactic astronomy, whether they're high school, college students, or just lay people, what would you recommend that they look into if they're interested in your mission or just the general field, to kind of get a better understanding of, what the kind of topics your spacecraft and payload are going to produce?
So the most obvious resource will be the website, which is spherex.caltech.edu. Caltech is CALTECH. That will have sort of high-level overviews and keep news and any sort of, public articles, things like that, will show up there. I think that the more interested people should look at the couple papers that we wrote as summaries for the community of these 2 workshops that we had over the years. Those are written at a, probably advanced undergraduate kind of level of understanding. And I think it would be really interesting for people to kind of have a look there, and it'll give you a really broad overview of the kind of science that SPHEREx is capable of.
And we have links to those in the blog post that will accompany this episode. They're actually really interesting reads that we went through before we sat down today.
Oh, wow. You guys did your research.
All right. Dr. Zemcov, thank you very much for speaking with us about SPHEREx. We wish you the best of luck in your future research. And this is a super cool mission, so I personally will be following this pretty closely up until 2023.
Great, guys. Thanks very much for having me. I appreciate it.
Thanks for listening. If you like this episode, subscribe to future episodes, and you can check out our huge backlog of past episodes and blog posts, including interviews with key people in the space industry, in-depth articles on spacecrafts and rockets, and commentaries on recent events in space on our website, blog.spexcast.com. Also, let us know what you think of the show. You can leave a review on iTunes or your podcast service, or reach out to us via Twitter at SPEXcast, or send an email to spexcast@gmail.com. Our music is by Nelson Scott.